Hello again. In this part of lecture, we will see what are hardware description languages, why they are used, or in a very simple terms, we'll try to answer this question that why we are using Verilog in this particular course. So before that, let's try to answer even simpler question: why do you use C, C++, Java or Python kind of languages? So you use these languages. They are also called high level languages because they are closer to English. You can represent or you can write your ideas in a more precise manner in any of these high level languages like C, C++, Java, Python, etc. And whatever idea you are representing, whatever idea you are writing, that is very precise, that will have definitive input and definitive output. Whatever you have written, that will not give two different outputs unless it is aimed or it is designed like that. Similarly, so overall we are writing in those languages to express our algorithms, to express our ideas, which would be executed later on a hardware, on a processor or an operating system in your computer systems. Now, in a similar way, instead of writing algorithms, I want to describe my hardware. What do we mean by hardware? Hardware means that we will have these logic gates, and we may have other hardware things, like we may have chips or some modules or some processors. So we want to describe them, and to describe them, we again, one method what we have been learning in this course is we can describe them by Boolean equations. Yes, of course, that's a fundamental method to describe these modules or these hardware units. However, when the hardware unit will become large or will have many more components, then this method will be insufficient. So we would also require to represent these units hierarchically, and like one unit can have multiple other smaller units, etc. Plus, there is a very definitive feature of these hardware units, that all of them would work in parallel. Okay, so this functionality behavior part is one thing. The other thing is because they will work in parallel, because all these units, because it's a typical nature of hardware that for example, you see you have a processor, keyboard, you see that all of them things looks like they're working in parallel, correct? Okay, so because hardware is working in parallel, this particular property is called concurrency. So we require a language, we require some sort of description which can also have these characteristics of concurrency. Okay, and they can also concurrency, whenever concurrency is there, then the notion of delay will also be there. How much concurrent, so whether there is some delay between one function and the other function. So we would require some sort of a language which can describe the function behavior, which can also model concurrency, which can also model delay. So that is why a separate sort of languages were invented. Okay, these languages are called hardware description languages. So the languages which are specifically designed to describe the hardware. Initially, this hardware description languages, like they were invented in early 80s, and then we got more or less confined in by the late 80s. So many of these languages were defined. So the idea of initial definition, initial invention of these languages was to describe in hardware or to model in hardware. So when they were the whole idea was that before actually implementing things in hardware, let us model them in software, so that we can verify, we can see whether it actually works or not. So that was the initial idea of hardware description languages. But in last 30 years, like after late 90s, late 80s, these hardware description languages are also popularly used to synthesize the hardware. Synthesizing hardware essentially means that once we write in hardware description languages, then we can have some sort of a EDA tool. EDA means electronics design automation tools. These EDA tools are essentially softwares. So these EDA softwares can take hardware description languages and can finally produce or finally describe the hardware in terms of logic gates, and using those logic gates we can do the later process of chip designing. So they are essentially now, in summary, we can say that these hardware description languages are also used to design hardware, not only model hardware but also used to design hardware. So what are the various options of these hardware description languages? There are many present in the market. So there are two very popular languages. One is VHDL, another is Verilog. So VHDL is strongly typed, verbose and deterministic. Strongly typed means that there would be, like, if there is one particular variable defined as particular data type, then it would remain as that data type. So you cannot so that type is very strongly defined. You cannot connect it to, or you cannot pass this as a variable to another one which is slightly different. So let's say unsigned int and int, they cannot passed on as a single variable. So verbose means for the same thing you have to write little more. Deterministic, all the languages has to be deterministic, that whatever function is being specified, it will always behave in the same way. So the result would always be deterministic. If you run it once, twice, thrice, it will always give the same result. The other popular language, hardware description languages, is Verilog. It is weakly typed, so and concise with efficient notations. So this particular language Verilog is mostly derived from C syntax, so that's why it is quite concise. Weakly typed means it can you can help with different kind of, you can connect different kind of data types, although there would be some restrictions, but yes, it is less difficult to write in Verilog with respect to in VHDL. So because of strongly typed, because of verbose nature, historically VHDL has been used in academia and Verilog has been used in industry. So because of this particular reason, we are also using because it's a industry oriented language, we would be using Verilog in this particular course. The other popular language is System Verilog. So System Verilog is a Verilog superset, means whatever are the characteristics, whatever are the syntax in Verilog, that will always be, that you can always use in System Verilog. Along with that, it can be used for a verification purpose. So there is some additional syntax which can be there in Verilog. So System Verilog is a de facto standard for verification of designs. Along with this, there are many other domain specific hardware description languages, like BlueSpec is a high level specification, even higher level than HDL. So Chisel, Handle C, System C, all of these are domain specific as well as even higher level of abstraction than HDL. So let us focus on Verilog hardware description language. In a Verilog hardware description language, the basic unit is a module. So now this module is equivalent to any hardware unit. How do we signify a hardware unit? So hardware unit will have some inputs, some outputs. Okay, and those inputs and outputs will have certain names. So these input and output for a hardware, it's also called ports. So there would be some input ports, there would be some output ports. So basic structure of a module or a Verilog module would be, you'll write module, then module name, and then you'll describe all the ports. Ports need to be declared. You need to tell that which particular port is an input port, which particular port is an output port. Then you will describe the behavior of the module, and then you can call end module. You can also treat this like a C++ class or a C function. So let us see how. Let's take some example and then see that how it works. So to take an example, I'm taking an example of a half adder. So there are two inputs A and B. There are two inputs A and B, and there are two outputs. One is sum, another is carry. So when input is 0 and 0, sum is 0, carry is also 0. When input is A is 0, B is 1, then sum output is 1 and carry is 0. Similarly, if A is 1, B is 0, then also sum is 1 and carry is 0. If both A and B are 1, then sum is 0 and carry is 1. So if we see from the truth table, then sum looks like a XOR gate and carry is an AND gate. So we can also write it like this: sum is A XOR B and carry is A and B. Now we would like to define a hardware module or a Verilog module to describe this particular functionality of half adder, and we'll also see how we can verify this functionality. So let us see how the Verilog module would look like. So in Verilog modules, like while describing the hardware or describing our description of module, there are two ways. One is a structural model, another is a behavior model. So we'll see both of these models, structure model as well as a behavior model, in this particular lecture. So now this is my module, a half adder, which will have two inputs, let's say A and B, and two outputs, sum and carry. So I would define my module as module half adder. In the parenthesis, I am writing all the ports A, B, sum and carry, and then I can also say then I need to describe what these ports are. So I have to say this A and B are actually of type input, and sum and carry are of type output. So this is our module name and these are our port list. Good. So now the description in structural model is, you see, we have to put them in the sort of list of connections between various components. Now in our previous slide, we have seen that half adder, in half adder actually sum is an XOR of A and B and carry is AND of A and B. So I can instantiate an XOR gate and then say that XOR gate, and the name of instance I have to write, U1 is the name of instance, and then the connections of this XOR. So you can also see it like this, that XOR will also be some other module like this, and it would have certain port list. So if I write the name of my input and output in the same order, whatever is the port list of that particular module, then it would get connected. So this sum would be connected to the whatever is the output of XOR, and A would be connected to first input of XOR, B would be connected to second input of the XOR, and U1 is the instance name or the object name. So you can see, you can visualize that there could be multiple XOR gates in our module. So each of them should have different names. So that's why this is the instance name. And similarly for the AND gate, we can use our another instance name and then connect the carry as the output, A and B as the input. So these AND, OR, XOR, etc. So these are all called primitive gates, or primitive gates which are available in our Verilog. So we can use any of these primitive gates. There are 6 primitive gates which are there in Verilog, and or XOR, NAND, NOR, and XNOR. Along with we have 2 buffer and NOT as the primitive gate, which are used for single input. All these primitive gates and or XOR, NAND, NOR, and XNOR could be used as a multiple input. So there could be a AND gate with multiple inputs. So that's why the port pattern, this port pattern is first the output, and after that all the inputs can be given. And this is true for all of these gates. Similarly, for the NOT gate, first port would be output and then input. Okay, so let us say after we have created this module half header, now this half header can also be used in some other module as a instance name. So then we can say half header and then module name, and then we can connect. So using this structural model, you can create a hierarchy key. In hierarchy key, you can create different components, and then you can use those components in higher level of abstraction, and keep on doing that till you can design your whole system. Okay, so this structural module is a very powerful way of modeling a circuit. It's very similar to way we do on pen and paper, that we create different models in terms of block diagram, and each block diagram further can be designed using gates, and each gates could further be designed using these primitive gates. Okay, so this is the way we do in a structural model. Another way of modeling the same thing would be in a data flow model. So in a data flow model, instead of specifying the structure, means instead of specifying the gate level components, we describe the behavior using Boolean equations. And all these Boolean equations, are use this particular keyword called assign. So in this assign keyword, we will write the Boolean equations in the same way we are writing in our while solving our questions, etc. The symbols what we have to use is, for example, for XOR we have to use this cap symbol, for AND we have to use ampersand, and for NOT we have to use this tilde symbol. For NOT we have to use this symbol, and for OR we have to use this symbol. So these symbols are used these symbols we can use for describing all the functions, and then these functions, these Boolean equations can be assigned to the output. So further this particular assign statement, for example, there are 2 assignment statements here, so both of them are happening concurrently. So because it's a hardware model, A and B, let's say there is a change in A and B, both of the change in A and B would be reflected in sum as well as carry at the same time. So this data flow model is also equally powerful like a structural model, because now instead of describing the whole instead of describing using basic gates, now we can use equations are sometimes more effective way of representing, because you need not to write each and every gate. So you can summarize all of these gates in form of Boolean equations, and then we can use them. And further, because of you can combine multiple signals in sort of array, so those signals can be combined and then can be assigned. So this all of these features make this data flow model also quite powerful. So we'll use this in some practice assignments, and then we'll understand. Now let us see how do we verify a Verilog module. So to verify a Verilog module, we also write another module. This is called test bench. So in this test bench, we has a very specific specific property that it doesn't have any ports, because there is no input, there is no output to the test bench. The whole idea this test bench is created is to instantiate our design under test, or basically we call it DUT. So this half header we want to test. So in the test bench we will instantiate some of the wires, some of the signals which will give input to these ports, and which will also receive the output, and we can then compare whether the output is correct or not. So that's the functionality of our test bench. So the other thing which test bench has to do, it has to instantiate our module which we want to test. So here half header is the module which we want to test. So what we have to do is we have to instantiate the way we had instantiated AND gate and XOR gate in our structural design. So we said that half header is the name of module, and the name of instance is HA underscore INST. So this is the instance of half header. Now in our previous example of structural modeling, we have simply written sum A B. Here we are doing a different kind of port binding. In the port binding we are specifying, so here order is not important. What we are saying that the A port is connected to RA signal of the test bench. So you see RA is in the scope of test bench, so there is no dot written here. But if you remember in our C or C++, whenever the scope is inside a particular module, so here half header is the module, and the scope of this A is half header dot A. So half header is implicit here, and dot A means the scope of this dot A is inside half header. So dot A is connected to RA of the of our test bench. Similarly, dot B is connected to RB of the test bench. Dot sum is connected to W sum, and dot carry is connected to W carry. So that's how we can make the connections, and this is also called port binding. So in this port binding we are connecting. So when we are using this particular style of port binding, it doesn't matter what is the order of ports, order of variables within this instance. Now you, for defining or for connecting or for giving the input, we have to define something RA and RB. So we have to declare those signals or wires. So the way these signals and wires has to be defined, we have to we are defining in our test bench, whatever is the input, we will define it as a reg type, REG reg type, and whatever is the output, we are defining them as a wire. Whatever is the output, that is defined as wire. Now you can question that what is reg, what is wire. So this reg and wire are a single bit structures, which is very similar to bool of C++, bool of C++, and the reg and wire, so they are, because they are close to hardware, so we are defining wire as a 1-bit structure which can carry a particular input or output. A reg is another single bit structure which can also hold the value. So because RA is a value which would be given to A, so it need to hold that value, so that's why we are using a reg for RA. Now let us see how do we do it inside. So now we have to instantiate, we have to give some particular input to our input RA and RB. So this RA and RB, all these inputs have to be given inside a initial block. So in the initial there has to be begin, there has to be an end. So in an initial block, so this begin and end are like starting curly braces and ending curly braces. and this particular module, this particular block is called initial. Initial essentially means that it would run first time or once whenever your execution will start. Now I want to assign RA as 0 and RB as also 0. So what is this 0? 0 means 1 bit. So since in Verilog you can also give input in multiple bits, so we have to define that how many bits it is. So and you can also give your input in form of binary, in form of hex, in terms of decimal. So that's why also it is important to specify whether it is binary, decimal, or hexadecimal to be deterministic and to be precise. So because RA is a single bit, so I am writing 1, and dash B means that it is written in binary. So this is the notion, this is the representation, this is the way we would be writing any constant input, or we will be assigning these constant inputs to any variable like reg or wire. So you will see that we have assigned 0 to RA, 0 to B. Now after some time, so this hash 10 means there is a delay element. So after a 10 units of time, there is no unit specified, so that means there is some unit which would be taken by Verilog by default. So after 10 units of time, then we would give RA will give another stimulus or another input to my RA and RB. So similarly, after each 10 units of time, we are giving different inputs to our RA and RB, which are our inputs. And then the question would be, how do we see what is the output? So for seeing the output, one particular method is we can use printf kind of a statements. So the printf in Verilog is written as a display. So it's called $display. So $display, and after that the syntax is very similar to our C. So you can say inverted commas A and then %B, that means the output would be written in binary form and output would be written in binary form. So it is very similar to that, and whatever are the variable names, so all these variable name you can write in the correct order. So this display would give the output, give this particular string it will give, and corresponding output would be generated. So this whole thing is called stimulus, and a display will give us the output or printf like output.